Alright, streaming is good. And we can start with the lecture. Alright. Good afternoon, everyone. Welcome back to the lecture. So how is it going? Assignment 2. Are you happy with your progress?
No.
Are you stuck, still thinking of the ideas, or what is the status?
I'm guessing it's a problem of we're not being used to working with something so complex on a low level.
Alright.
Like implement our own lighting system, make gravity not annoying, stuff like that.
So there are like too many components for you. There will be a help session actually in like 3 weeks, the very last lecture, where we will have opportunity like to discuss all those stuffs and get all the help you need before starting the holidays. So you will get the help, but if you have like some particular question before that, you can approach anytime or like open an issue or something like that. Alright, we should have had a demo from Tom, but apparently he's late, so I have another demo that I can show just as a motivation and inspiration. That is pretty cool, I think. So this is from last year, but still very impressive. So it's a demo from NVIDIA and Microsoft. It's kind of common framework, and it just demonstrates one of the state-of-the-art real-time ray tracing, reflections, and the photorealism. So you can enjoy that. So this is all done in ray tracing, and they claim it's real-time.
I heard Kylo Ren destroyed the one over in D sector.
If you ask me, who's ever in charge of this place should be transferred to Hawk. What?
Bolus system?
I'll show you after the video. There is in the description.
You think she heard us?
Yeah, I think she heard us.
At least we blend in for once.
Pretty impressive, right? And yeah, if it's really real time as they claim, that's pretty scary, and it can be interesting for gaming, like if you have this kind of photorealism in gaming. So it's actually using Microsoft's new DXR framework, and NVIDIA is kind of participating in this, and ILMX Lab is, I think, the producer of the stuff. But it was just like 1 minute demo released last year, so hopefully we will get something like full scale soon. So have you seen anything like since then, something like that, even like larger scale?
Well, there's the other one we were hovering over now. They have released a lot more demos for the same sort of thing, but not in the grand scale yet. No.
Oh, okay.
But one of the critiques we raised when we saw this last year was that it
Very
was all
short.
pretty much enclosed in a tiny area, right? So
Oh,
you don't
yeah.
have the large scale in terrains or stuff. Even the outdoor bit was really sort of
Oh yeah, occluded. Yeah, because if they have large scale area, that will be too much computation. That might not be feasible in real time so far.
But I think that's sort of what they try to go towards in the second demo you have right there.
This one?
Yeah, I think they have a larger sort of area, but I don't really know how to
Okay, yeah, just.
which one that one is. Yes, it's probably
At some point it's like really difficult to distinguish what is kind of computer generated and what is actually captured by video, because the photorealism is really good. Because something like the idea. Oh yeah, outdoors. Wow, the background is still static.
yeah.
It's not much happening there.
Of it was in real time. This is not a movie.
Well, yeah.
This is next generation graphics. This is what RTX enables. This new form of computer graphics that brings together rasterization.
Well, a bit of inspiration, and we can get back to our topic. Let me check that streaming is good. Yeah, the video is good. Alright, our today's topic is shadows. Any ideas? What are shadows? What does this word say to you?
A shadow is when the level of light is distinctively lower in an area.
Yeah, cool. Any other contribution to defining shadows? Yeah.
Area where light coming from the light source is blocked by the.
Yeah, exactly. So it's occlusion or obscuration of the area by an object from the direct light source. So here we have a few definitions, like volumes of space that receive no or light that has been attenuated through obscuration, what you have said, covering by some object from the light source, redirection or transmission, or from Collins dictionary with like more neutral definition without technical context. It's a shadow is a dark shape on a surface that is made when something stands between a light and the surface. And shadows are very important for photorealism, as you have seen in the demo. Like reflections, shadows make it very similar to what we encounter in our daily life, because without having proper shadows like that we see around us, it will not be really realistic. And shadows actually have lots of information encoded. Like for instance, what does this photo tell you? Like what information can you extract from this one? You can get pretty much, right? Even though you don't see any scene directly. What do you know from this one?
Well, there's 6 people. The one in the center is tall, and then one's on the side.
Yeah.
Understand means something.
And any information about illumination? Where is the light source? What is the lighting geometry?
Light sources like directly behind the camera.
Yeah. So it's like pretty rich in terms of information, but sometimes it can be like confusing, but still like our brain has some adaptation or predisposition to interpret the environment. For instance, what do you see here? Is it a crater or a hill? So crater or a hill? Any ideas from there? So is it something like a hole in the ground or something that rises from the ground?
I don't see like one big crater and then a small hill in the middle of the crater.
Oh yeah, so this is a big crater and there is a small hill inside. Okay, if we just flip this image by 180 degrees, exactly the same image, what do you see now?
The opposite.
Yeah, so you see this as a hill and then you see this as a crater, right? So yeah. The explanation for this proposed in the literature is that on the Earth, like we are used to having the light source coming from above, and in these kind of situations where it's not very clear, we assume, our brain assumes that light source, the lighting should be coming from top. So in this case, considering that we have this side lit and this side dark, we assume that the light comes from here and it hits this side, does not hit this side, so it should be the hole. And the other way around, if we have a look here, and this side is darker and this one is brighter, we assume that if it comes from here, it should be a hill blocking the light to reach this side. So it's kind of assumptions our brain does automatically without our will. And here is another explanation, like another demonstration of that one. Like those ones, so in both cases, our brain somehow assumes that the light is coming from top, and those ones look that something that rises from the surface, and this one is darker because it doesn't get to here. While here, if the light comes from the top and reaches bottom, but not this part, it should be something like the hole. So shadows include much information, but when we don't have any shadows, then it can become confusing. Like in this case, the front face, is it bottom of the back face or up of the back face? So can you decide and say for sure either way?
It looks like something I folded in or something origami on.
Yeah, but see, because we're missing the depth cues, you can't really say that, okay, this is the front side and that is the back side, or the other way around, that this is the front side and this is the back side, right? It's kind of bistable. Those kind of images are called bistable, where you can see two states at the same time and you can decide. But even if we have shadows, if they contradict each other, if they are not in a logical way and do not actually make sense because one shadow contradicts another one, it can be very confusing for our brains, like this one. So which cube is front and which is kind of inside? So which comes out from the forward and which is back part? It's a great example of having something bistable. Like you can really focus on either of them, right?
Yeah.
But
oh, okay. I thought it was just.
So how do you see it?
I thought they like the holes protruding outwards.
Yeah, you can see it either that way, or you can say the other way around, that the bottom is kind of outwards and the top is inwards.
Yeah.
So both of them are kind of right, because there is the cue that, okay, this one is out because of this shading if the light is from this side, but then it can be also possible that this one is inside and the light comes from this side. You have no information about illumination. That's what makes it confusing. And in this case, actually, the thing is that all those squares are located on the similar places, but because they play with these shadows, so which of them looks closest to the surface and which of them looks floating up in the air? So, do you see any difference in that terms? So
the further away the shadow is, the further up it looks like it is.
yeah, exactly. So cool. So as we have the shadow spreading farther away, and this one is closer, our brain interprets that okay, there is somewhere the illumination, and because this is higher, the shadow is larger, and the other way around. Because the shadow is shorter, it means that this one is close to the surface. Yeah, and I think you are all familiar with this one, are you? So, who doesn't believe that color of the A square and color of the B square is the same? It's exactly the same color. What? Do you agree? Or so what do you see?
I see a white B and a gray A. Am I stupid?
That's normal, actually. Your vision is tricked because it's exactly the same color.
Okay.
Yeah, here the explanation is that there is a color constancy, the capability of our vision to discard effects from environment to see colors more or less constantly. Like, for example, if you measure the color of those walls here, they will be grayish, and if you show that to a person like a patch, they would never say it's a white. But considering that you understand what's going on here, you understand that okay, there is shadows, there is no direct sunlight, your brain tries to discard this effect, and you say that okay, the walls are white in this room. So something similar is happening here. So even though this has the same color, your brain interprets that okay, this darkness, similar being the dark as this one, is due to this shadow because it's located in the shadow. That's what makes it dark. But if I discard this shadow, this should be brighter and lighter, and that's how your brain is and vision is tricked, and you think that okay, I should discard this kind of dark tint due to the shadow because its true color should be lighter, and you see it lighter even though if it isn't. And yeah, and similar things happening here, like this color and this color, is it the same? Yeah, it's the same. It's the same logic. Like, you think that this is dark because there is no direct light coming, so it's dark due to the shadow. So you're trying to discard this shadow and see it as white. But actually, if you see without context, it's exactly the same color. And the last one here, sometimes if you don't have enough cues, for example, where the light is coming from or why do we have this shadow, you might think that this lady is floating in the air. So you might assume that light is coming from the top, as we are predisposed to. So it's something like floating. And shadows can contain pretty rich information about the material itself. So this one is the real objects that we have here on the lab, and this is from my experiment. And considering those shadows, you can like see and conclude lots of things. First of all, you see that okay, This is kind of round spherical object, something like that. You see that part of the shadow is bright because it should be transmitting the light, while here it's very dark because you can guess that this one does not transmit any light. And here it's a tiny little bit of bluish tint, so you see that, okay, this transmits some amount of light, but not as much as those ones. And also the color, you can guess, okay, this is orangish, amber, this is yellowish color, bluish. So the shadows are very rich in terms of information and might be very important to interpret the scene and the environment. So light isn't everywhere, and shadows are important in human vision that we already have seen. And with shadows you can interpret like height, depth, shape, lots of information about the scene. And there are two categories of the shadows in a very general sense. One is when the shadow falls on another object, so-called like Peter Pan shadow. For example, the shadow of one object falls on the wall. And another one that is more difficult to fake is the shadows on the object itself. For example, if I take this one, right, it's better example like this one. There are lots of shadows on the same very object, like due to these shapes, I have shadowed in these deep areas and like this side because the light is coming from that side. So it's self-shadowing of the same object. Well, yeah, one question. Which properties or techniques we have seen so far can somehow emulate shadows without actually modeling shadows? If you try to recall the textures lecture or lighting lecture, there was one trick that could have this shadow-like result. We have gone through that. So which technique was that? Something with playing with normals and having impression of bumpiness on the surface. No idea. Try to guess whatever you remember from textures lecture. What was that?
Could you repeat the question again?
Yeah, sorry?
Could you repeat the question again?
Yeah, which technique or functionality we have discussed so far within the course, and I will give you a clue that it's from textures lecture, I think, can emulate shadows. So without explicitly modeling shadows, it can give kind of comparable result. It can show some shadows, and because of those shadows you see some bumpiness and roughness on the surface. So it's kind of similar to self-shadowing object, and you get there by playing with normals without explicitly changing the geometry. It's bump mapping. So we have this very smooth sphere and we have a bump map, so the darker areas that should look kind of holes, and lighter areas should look higher, but actually it's not geometric change, we just play with the normals, and finally we get this kind of rough appearance with this spot looking like a crater or a hole, and we have lots of shadows on the surface that tells us that, okay, we have roughness on the surface. And yeah, another thing, maybe another trick that was also very useful, normal mapping. So do you remember what normal mapping was? So what are normals? Let's start with that. Why do we need normal information? Well, what is normal?
What we assume to be commonplace.
Sorry?
What we assume is the most common.
Not in that sense, but in terms of graphics. Yeah, that was the right answer, but not in this context. Okay, what are normal vectors? So they're perpendicular to the point, and they are used to what? Several reasons. First is to identify whether the face is looking, like so facing towards the observer, or it's kind of back face. And the second one is to just like define what are the reflections of the light. So we have incident angle. Let me draw here. So we have some surface. We have a normal vector that is perpendicular towards this point. And we have some incident light, and the angle between incident ray and the normal and the reflected ray and the normal should be the same. So we get the direction and we know where the light is reflected. So if we know where the light is coming from and we know the normal vector, that is nothing but the vector that has 90 degrees with the surface, we can know where this ray is reflected. So if this comes this way and this goes backwards, like towards this way. And the angles, this angle and this angle are same. So what is the trick here? Let me show you something. Wow, this one, yeah, it's pretty impressive. Oops, sorry. So any guess what's going on here?
Oh, there's a light source that's moving around.
Yeah, that's true. Cool. And do you see any difference from this side and something interesting happening there?
So they sort of look flat on the right, but they still receive the lighting.
Yeah, that's true. That's very kind of good direction, right direction. Yeah. Well, the thing is that the ones on the left are actual 3D, and as you see, there are some shadows. But when you see like this one moving, you see that the right side is flat. So theoretically, this should be all white, because if it's flat, where all those shadows are coming from. But the trick is that we have normal mapping. We take normal information, so we take those informations, and we take those normals and map to this side, and we get this effect that looks pretty impressive. So the light that hits the left side and is reflected this way and is encoded as a normal that we have here. So we move this information and put on this side, and it behaves like it was reflecting the light as it is on the left side. So using the normal mapping, taking the normal vectors from here and mapping to that side, we can have this kind of 3D-ish perception, even though this is geometrically just flat. So that's a trick with normal mappings, that you can use shadows for 3D perception. But when it moves, you see that it's flat and it's just something like tricky happening. All right. So what can be difficulties or challenges when you are trying to model lights and shadows? So imagine you have to model shadows. What are the problems you might face? So anything that comes to your mind.
Performance
Yeah. Why performance? What can be too much to be calculated? Which information?
Like kind of a thing. If there's multiple shadows on the same spot.
Yeah, that's true. So lots of different directions where the light is coming from. Yeah, this looks like this from complicated, slow but more realistic to simple, fast but not very realistic. So like let's start with directional light. When you have like just directional light rays coming from some infinite location and you have an object that is obscuring, you have hard shadows. So you have this area dark because it doesn't get any light, it's black, and you have those light areas illuminated. Or if you have just point light source that spreads light this way and you have this one obscuring, this one is black because you don't get any light here, and this one is illuminated. But this is theoretical and a very simplified version. What happens is in reality, for example, like those ones, this is area light source spotlight, or area that you kind of has its area and spreads the light all around, right? So when you have the area or spotlight, if you say it the other way, you don't get this just like one ray coming to this direction, but you have like some gradation in shadows. This area doesn't get any light still, so it's still black, but for these areas, you get some light. You don't get this ray coming here, but you get something coming from here, you get something coming from here. So this is lighter than this, but still darker than this that gets all the light from there. And the one that is closest to reality in this case, when we have not only direct illumination, but indirect one that's happening in our daily life. So we have like, right now, even if we turn off all those lights, it will be still visible and everything will be like more or less possible to be seen, right? Because we don't have sun, but we have indirect illumination. The sunlight is reflected somewhere and coming through the windows to this room. So something similar is happening here. Even though those direct rays do not reach this area, those rays hit the walls, they're reflected, and they come here indirectly. That's why we don't have shadows that are very, very sharp, bright. So even if you look down the table, it's not black because there is still some light reaching it through the walls or through other objects. So in reality, illumination is very complex. You have lots of different paths where the light rays reach the direction. So these ones are called soft shadows, that is kind of gradually changing, and those ones that is illuminated or black is called hard shadows or sharp shadows. And here's the equation that looks scary at first, but it's very simple actually. So what we have here is that without shadows, the illumination is equal to global ambient light. So what was ambient light again? From the lighting lecture. It was
This is embarrassing because I've actually been programming these kind of light sources.
yeah, you are doing, I'm sure, in OpenGL.
Yeah.
I also feel a little bit embarrassed because I'm hearing the word ambient almost every single day, but I'm totally backing out on the actual explanation for it.
Ambient, diffuse, specular, all this kind
Yeah.
of stuff.
True. So ambient is kind of base light that is considered to be there without any particular directionality. So it's the same everywhere and it doesn't come from one particular direction. And then we just sum all other lights, that is like distance, the brightness, in this case spotlight, and we just sum like if there is any ambient coming from this one except for the base light, any diffuse illumination and specular light. So we all, like in the Phong model you have tried, I'm sure, where you add all those ambient, diffuse, specular together to have one final Phong reflection. So this is the same, but what's different here? Just one component is actually different when we have shadows introduced. This one, this component, and what this component does is that it just shows the portion of the light that reaches this particular spot. If we assume that here without shadows all light reaches the destination, here we have some kind of parameter that shows that, okay, half of the light is coming to this point and all the rest is occluded or obscured somewhere else. Well, why don't we have this parameter in front of this one? Okay, we have shadow parameter with this diffuse and specular light source. Why don't we have it with the ambient? What was ambient again?
Ambient is just general light that doesn't have any direction.
Yeah, and therefore,
so it doesn't cast any shadows.
Yeah, it doesn't make any sense to have this parameter that shows how much of it is coming. Yeah, that's true. So it's just a fraction that shows how much light is received. So for point light source, point light source is this one. It is kind of binary, either lit or black. But if it's area light, it's the range from 0 to 1, because you can have some partially illuminated areas like this one and this one here. That's more or less, yeah. And ambient light actually is used as a shortcut to approximate indirect light. In some cases to have a shortcut and simplify the situation, instead of modeling all the indirect illuminations and all the ways the light bounces from the walls and coming to the shadowed areas. You just take some base light, ambient light that is always there, and that's how you kind of trying to approximate this indirect illumination. And what factors influence shadows, like light source, whether it's directional, point, or area? So in which case do we have more kind of gradual change, and in which of these cases do we have very sharp, bright or dark black? So for those light sources, for point light source, do we have gradual shadows, or do we have just like dark or light, black or white, let's say? So point light source is, this one. So what kind of shadows do we have here? Any input from there?
Just black or white?
Yeah, that's true. Just black or white. But for area, we have these partially illuminated areas. It can be light transfer, whether the light is coming directly or it's indirect, reflected from somewhere. Material, like translucency, as we have seen when it's going through the object, or refraction. We will get to refraction by the end of the lecture. And geometry, whether it's simple shape, like a cube, or whether it's something very complex shape that is internal reflections and shadows and so on. And yeah, common limitations is that usually they don't support transparency. It's difficult. It's kind of problematic for shadow algorithms. Also, no indirect light. Well, you can have indirect light model, but it's very complicated. And as we have seen, what is used instead as a shortcut. So instead of modeling all light that is coming indirectly, what do we use as a shortcut to approximate it? the thing that we were just discussing that doesn't come from particular directions. Ambient light, yeah. And atmospheric effects like mist or these light rays through the dusty area. And also we work on optical level, so no wave properties of light are considered. For example, what is a phenomenon over there? Maybe you remember from your physics classes. So when the light hits a tiny little slit and it becomes like this pattern. It's diffraction.
I didn't know physics.
So yeah, these kind of things are not really modeled with the algorithms, and challenges are like first identify whether object is located in a shadow or not, and identify how much of the actual light is reaching to this direction, to this particular point. And yeah, maybe this one, and we can have a break. So it's mostly 3 groups. For lighting, for instance, like Phong model is a basis that is very widely used and is very convenient. But for shadow algorithms, there are lots of competitive, lots of algorithms competing with each other. There are lots of them with all their pros and cons, but there are like 3 different groups. Like object-based ones, the one that you just take the object, consider how it obscures the light and model that. Image-based, that you take the information of the entire scene. And the hybrid one where you take like some parts of both approaches. So anything familiar from here that we have discussed previously?
Shadow maps, we talked about that.
Yeah, maybe very briefly, because today I'm gonna go into details. Something that we talked pretty much about, not too much, but we kind of discussed pros and cons and stuff.
Ray tracing?
Yeah, ray tracing. Great. And yeah, that's more or less it so far. Yeah, it's like just primarily boils down to performance. So depends what is your task, what you want to do, and how each of those perform on your available framework and hardware infrastructure. But they're like all coming with their pros and cons. All right, let's take a quick break and then continue in 10-15 minutes.